Welcome to the deep dive. Stop for a moment and just think about this. Every single day, you're surrounded by this invisible, really powerful force, electricity.
Hmm.
We plug in our phones, flip light switches, maybe use power tools, and, well, often we don't give a second thought to the sheer energy we're dealing with.
Right. Or the complex systems keeping us safe all the time.
Exactly. We sort of just take it for granted. So today, we're pulling back that curtain. This deep dive, it's all about electrical safety, and we're getting our insights straight from Chapter 12 of this really good document we found called Electrical Safety.
Yeah, it's quite comprehensive.
It is. And our mission for you, listening in, is basically to give you a shortcut, a way to grasp the fundamentals of electricity, the main hazards it can present.
Which are significant.
They really are. And crucially, the really clever methods and devices we use to control those hazards. So by the end, the idea is you'll feel more informed and honestly just more secure around this force that's everywhere.
Okay, let's unpack this. What's fascinating here is how understanding just these basics can genuinely change how you see everyday safety.
Hmm.
It shifts from just, trusting things work to actually getting why they're safe. And that knowledge, well, it's incredibly valuable for just getting around in our electrified world.
I couldn't agree more. So, okay, this source, it really goes deep into the absolute basics, the bedrock of understanding electricity.
Right.
And the first principle it lays out, Ohm's law, that struck me as, well, just incredibly fundamental.
Mm.
Can you help us unpack why this equation, IVR current, equals voltage divided by resistance? Why is that so key for electrical safety?
That's a great question because Ohm's law, it really is the foundation. It tells us basically that for any given voltage, the lower the resistance is,
Yeah.
the higher the current will be. And it's the high current, not always the high voltage, that actually does the most damage in many situations.
Right, I see.
So understanding that inverse relationship, low resistance, high current, it's absolutely key to grasping how dangerous a circuit can potentially become.
Okay. And building on that idea of current and resistance, the document then brings up Joule heating, which honestly sounds a bit like something from a sci-fi film.
Yeah, it does sound a bit dramatic.
But it's very real, isn't it?
Oh, absolutely. And it's often the hidden culprit behind a lot of electrical fires. Joule heating, it just explains why things get hot.
Simple as that.
Pretty much.
Hmm.
When current flows through any material that has some resistance, it generates heat. And Joule's law puts a number on it with the formula PIIR, where P is power in watts.
The CIIR.
Okay. What's really critical here, the thing to remember, is that the heat generated is proportional to the square of the current.
The square. Wow.
Yeah. So this isn't just some abstract formula from physics class. It means even a small increase in current can exponentially ramp up the heat generated.
Exponentially. Okay.
Which means a slightly overloaded wire can go from just warm to dangerously fire starting hot really, really quickly. In a flash, sometimes.
That's quite a stark reminder of those invisible forces.
Yeah.
And then, okay, there's arcing. This isn't just the cool special effect you see in movies, right?
Mm-hmm.
The source points out it's actually incredibly dangerous.
Absolutely. Arcing is basically when electricity jumps the gap, when current flows through the air between two conductors.
Through the air.
Yeah, it creates this incredibly intense burst of heat and light. And arc flash, the danger isn't just the burn from the arc itself, though that's, severe.
Mm-hmm.
But as the document really emphasizes, arson can be a major ignition source. It can start fires or even trigger violent explosions, especially if you're in an environment with, say, flammable gases or dust.
Which leads us straight into the primary hazards,
Yeah.
the things we really need to watch out for. The document lists the most common ones.
Yeah.
Electric shock, fire, and explosion.
The big three. Yeah.
Electric shock is probably the one most people think of first.
Yeah.
It happens when a person accidentally becomes part of an electrical circuit.
Completes the circuit, yeah.
But the severity of that shock, it isn't just random, is it? It depends on a few key things.
That's right. It's not just about voltage, though. That plays a part. The severity really depends on the amount of current flowing through the body.
Cool.
The voltage driving it, the type of current, and interestingly, AC, alternating current, is generally seen as more dangerous than DC, direct current.
Oh, really? Why is that?
Well, it's fascinating. DC might cause, a single strong muscle convulsion, which could throw you clear. But AC, because it alternates, it can cause sustained muscle contraction. Tetanus.
Meaning you can't let go.
Exactly. It makes it incredibly difficult, sometimes impossible, to release your grip on a live conductor. And worse, it can disrupt the heart's rhythm, causing it to fibrillate.
Vibrillate.
Yeah, ventricular fibrillation, where the heart muscle just quivers chaotically instead of pumping blood.
It's not just about the raw power, but how the current interacts with our body's own electrical system. That's what really defines the danger.
That can't let go threshold is terrifying to think about.
It is. Our source highlights just how specific the effects are based on the current level. Very low currents, like around 1 milliamp. You just feel a tingle. Yeah. That's the perception threshold.
Right, just noticeable.
But you increase that just a bit, say around 16 milliamps for men, and you hit that can't let go point you mentioned where your muscles just contract involuntarily.
And it gets much more serious very quickly from there. The document points out that currents passing through the chest area, even as low as maybe 50 to 100 milliamps.
That sounds tiny.
It is shockingly small, isn't it? But that can be enough to cause that ventricular fibrillation we talked about, the heart just quivering uselessly. And then, of course, at higher currents, you get severe tissue burning, which can be disfiguring or, well, fatal.
So beyond the immediate shock danger, there's heating and fire. And this often comes from situations we might not immediately think are risky.
Exactly. This often comes back to overloaded conductors or maybe poor loose connections or electrical shorts.
Right.
Think about that Joule heating we discussed earlier, PIRR. All those scenarios, overload, bad connection, short circuit, fourth circuit, they cause excessive heating. That heat can then easily ignite nearby combustible materials, wood, insulation, fabrics.
And it's a common cause of fires.
Sadly, yes. Electricity is a leading cause of fires, both in homes and in commercial buildings. It's a significant concern.
And then perhaps the most dramatic hazard, explosions. This links back to arcing, like you said before.
It does, yeah.
Yeah.
If you get an arc, that electrical jump through the air happening in a place where there are flammable dusts, like maybe in certain factories, or even a grain silo.
Grain silo.
Or flammable vapors, that spark from the arc can trigger a really violent explosion. That's why you need specialized explosion-proof equipment and extreme precautions in those kinds of hazardous locations.
Okay, so given these pretty serious hazards, shock, fire, explosion, the real core of this deep dive is understanding the controls. How do we manage these risks? Often without us even realizing it.
Right, the invisible safety net.
The document breaks them down into several, honestly, quite ingenious categories, starting with physical controls.
Right. Think about the tools and appliances you use every day. They're often designed with multiple layers of protection built right in. One key physical control is isolation and double insulation.
Double insulation, like on my power drill.
Exactly like on your power drill. It involves cleverly enclosing all the live, energized components and then using non-conductive materials, that's the insulation, to separate people from those live parts. That double insulation gives you an extra layer of protection, almost like a safety bubble around the electrical bits.
Okay, and for those really hazardous situations you mentioned, like with flammable gases, what kinds of physical controls do they use there?
So in those very specific classified hazardous locations, electrical equipment often has to be sealed or rated as explosion-proof.
Explosion-proof, got it.
The goal there is basically to contain any potential sparks or arcs inside the equipment, preventing them from ever igniting that flammable atmosphere outside the equipment. It's all about containing the danger right at its source.
Makes sense. Then we move on to overcurrent devices. These are designed to, well, cut the power if the current gets too high, right?
Precisely. To protect the circuit, we all know fuses, the older style.
Yeah, the little glass things that blow.
Right. They contain a little metal strip that's designed to just melt and break the circuit if it gets overloaded. Simple, effective.
And the modern equivalent.
Circuit breakers, which are basically more sophisticated switches. They automatically trip or open when they detect an overcurrent condition.
And you can just reset them.
You can, which is convenient, yes. But their primary job is safety, protecting the wiring from overheating, protecting your appliances from damage, and crucially, preventing fires caused by those overloads.
Okay. Next up, switching devices, which seem really important for, like, maintenance or repairs. Lockouts.
Yes, lockouts are critical. They are literally physical locks placed on a switch or energy source.
Like a padlock.
Often, yes. To prevent anyone from turning the power back on while someone is working on the equipment downstream, this is a huge part of what industry calls a lockout tagout, or a LOTO procedure.
Why is that procedure so vital?
Because it ensures, absolutely positively, that the equipment is de-energized and cannot be accidentally re-energized while maintenance is happening. It locks out the energy source, preventing really tragic accidents.
Right. Prevents nasty surprises.
Exactly. And interlocks are another clever safety mechanism you find. They're switches designed to automatically cut the power to equipment when, say, an access door or a protective panel is opened.
Like on a microwave oven.
Perfect example. It's a fail-safe, making sure you can't easily access live, dangerous components while they're still powered up.
Okay, now two really important concepts. Ones I think people often mix up, grounding and bonding. I've heard them used almost interchangeably, but the source makes it clear they're different, right?
They are different, yes, though they often work together. Bonding is about connecting two or more conductive objects together with a wire or strap.
Why do that?
To equalize their electrical potential, their voltage, it's often used to control static electricity buildup, basically preventing sparks by not letting a charge difference develop between objects.
Okay, so bonding equals equalization. What about grounding?
Grounding is connecting one or more of those objects directly to the earth, usually via a grounding rod or the building's grounding system,
And the purpose of that?
to provide a safe path for electrical charge, especially fault current, to flow away harmlessly into the earth. A proper equipment ground wire gives fault current a dedicated, low-resistance path to follow, ensuring that a person doesn't accidentally become that path if something goes wrong, like if a wire comes loose inside an appliance and touches the metal casing. That's where the real danger lies. Grounding gives that dangerous current somewhere safe to go.
Okay, that makes sense. Grounding is the safety escape route.
Essentially, yes.
And maybe one of the most, ingenious safety devices for everyday people, something we see all the time now, is the ground fault circuit interrupter, the GFCI.
Ah, yes, the GFCI. Truly an invisible guardian.
They're in our bathrooms, kitchens, outside. How do they work their magic? They seem to react so fast.
They are incredibly fast. GFCI is basically a super sensitive, super fast-acting circuit breaker. What it does is constantly monitor the tiny difference in current flowing out on the hot wire and back on the neutral wire.
Okay, it compares them.
Exactly. In a normal circuit, those currents should be perfectly balanced. But if a ground fault occurs, let's say current starts leaking, maybe through a person who's touched a live part and is also touching something grounded like a wet floor.
Right, the classic bathroom scenario.
Precisely. The GFCI senses that imbalance, that leakage, even if it's just a few milliamps. And it shuts off the power in as little as maybe 140th of a second, 0.02 seconds.
Wow, that's incredibly fast.
It is. Fast enough to prevent a serious, potentially fatal electric shock. And that speed is exactly why GFCIs are now required by code in places like bathrooms, kitchens, garages, outdoor circuits, anywhere. The risk of a ground fault, especially involving water, is higher.
It really is astounding how quickly they can react.
Okay.
Finally, let's just touch on static electricity. We mentioned bonding helps control it,
We did.
but our source clarifies something interesting.
Yeah.
The main hazard from static isn't usually the shock to a person, right? It's something else.
That's a really common misconception, yeah. While getting a static shock, like touching a doorknob, can be, annoying or momentarily painful.
Definitely annoying.
Right. But the main hazard, especially in industrial settings or places handling flammable materials, is the static discharge creating an arc, a spark.
Like the arcing we talked about earlier, but tiny.
Exactly. A tiny, unwelcome lightning bolt. And that tiny spark can be enough to ignite flammable vapors or combustible dusts, leading to a fire or even an explosion.
So the control for static comes back to grounding and bonding again.
Precisely.
Yeah.
It's elegantly simple, really. Bonding prevents the charge difference from building up between objects, and grounding provides a path for any accumulated charge to safely dissipate into the earth before it can build up to a level where it could cause a dangerous spark. It removes the ignition risk.
So, okay. We've taken quite a journey here, a real deep dive into the basic principles of electricity, the pretty serious hazards it can pose, and maybe most importantly, these incredibly clever, often invisible control mechanisms and safety devices that protect us constantly. Understanding these things, it really does empower you, doesn't it?
Right.
Lets you appreciate the layers of safety built into our world.
It really does. And this raises an important question, I think. When you consider the sheer power of electricity and the potential dangers we've just discussed, it's actually remarkable how safe it generally is in our homes and workplaces.
Yeah.
And that safety record is really down to this unseen engineering, these layers of protection we've been talking about.
Exactly. So for you, listening right now, think about this the next time you say, plug in your hairdryer near the sink or use a power tool out in the garage, just consider for a second that invisible engineering that's protecting you. Think about that GFCI outlet ready to cut the power in, what, 2/100th of a second?
Incredible speed.
Or the unseen work of the grounding system in your walls, just waiting to guide any dangerous fault current safely away into the earth. Electricity isn't just this potential threat hovering around us. Thanks to these incredible, meticulously designed safety protocols, it's become a reliably safe and, frankly, indispensable part of modern life.
So maybe think, what's a common electrical device you use every single day where you can now appreciate those hidden layers of safety working for you?